In everyday chemistry, the same organic compound can be given multiple different names. To help prevent confusion, chemists use a standard naming system to ensure that every organic compound has just one clear, unambiguous name. This system is called IUPAC nomenclature, and in this video, I'll show you how it works so that you can confidently name organic compounds yourself. IUPAC stands for the International Union of Pure and Applied Chemistry, and it's this union that has come up with an internationally agreed system that gives organic compounds a single systematic name. The purpose of this system is simple. The name of any compound should clearly describe its structure. To achieve this, IUPAC names are based upon the structure of the molecule itself, starting with the main carbon framework and then adding information about what's attached to it and where. This system allows chemists around the world to communicate clearly and unambiguously about any organic compound just from its name. And because the name is systematic, it means that there's a clear set of rules or steps we can follow when naming organic compounds. The first of these steps is determining the stem of the name. And to do this, we need to count the number of carbon atoms in the longest continuous chain that contains the main functional group. The number of carbon atoms in this chain then determines the stem. Now, you've probably already come across and used some of these stems when naming alkanes and alkenes previously. If there's just a single carbon atom in the chain, then the stem becomes meth. If there are 2 carbons, eth, 3 carbons, prop, and if there are 4 carbons, bute. At this point, if you can name shapes, you can name the subsequent carbon chain stems. If you've got 5 carbons, then the stem becomes pent, as in pentagon. And if you have 6 carbons, then the stem becomes hex. Now this convention continues for 7, 8, 9 and 10 carbons with hept, oct, non and dec. But AQA do explicitly state that you only need to know the first 6. So let's apply this to a few examples. Now at this point, all we're interested in is finding the longest continuous chain that contains the main functional group. So here we've got a nice simple one to get us started. We only have one possible carbon chain, and that's the one going straight across containing 3 carbon atoms. Because our longest chain containing the functional group, which in this case is our carbon-carbon single bonds, has 3 carbon atoms in it, it gives us the stem prop. Next up, we have a slightly trickier example. Now you might be tempted to think that the longest carbon chain is 4 atoms long, but we need to bear in mind that the chain doesn't have to be a straight line. In this case, we've got a cheeky kink in the carbon chain at the beginning, giving us a carbon chain length of 5. And you might be tempted to stop there as we've reached our hydroxyl functional group. But remember, the step asks us to find the longest continuous chain that contains the functional group, not that ends in it. We've got another bend in the chain towards the end of our molecule, which actually gives us the longest continuous chain of 6 carbon atoms, making the stem hex. Example 3. Well, the eagle-eyed amongst you have possibly spotted that our longest continuous carbon chain is 6 carbon atoms long, having taken into account those bends in the carbon chain. But we need to remember that we're looking for the longest continuous chain that contains the functional group. In this case, our functional group is the chlorine atom, and if we use the 6 carbon chain, the chlorine atom isn't actually attached to any of those carbons. So instead we have to settle for the 5 carbon chain, which although it isn't the longest possible chain, it is the longest one that contains the functional group. And as there are 5 carbon atoms in it, we get the stem pent. For our final example, we've got an alkene double bond as the functional group. With alkenes, you're generally looking for the longest carbon chain on either side of the double bond and joining them together like so. In this example, my longest carbon chain containing the carbon-carbon double bond is 5 carbon atoms long. So again, we have the stem pent. Now that we've identified the stem of our name, the next step is to identify the main functional group within the molecule. This is important because the functional group determines how the molecule behaves chemically, but also identifies the homologous series that the compound belongs to. And once we know the homologous series, we can then determine whether the name uses a prefix, a suffix, or both. Now, this builds directly on your understanding of functional groups and homologous series, so make sure you're comfortable with those before moving on. So let's have a look at our first example. Here we've got a molecule with a carbon chain length of 3, which gives us our stem of prop. Now, looking at this, you might immediately think that there aren't any functional groups within this molecule, but that's not quite true. We've got carbon-carbon single bonds as the functional group, telling us that this molecule is an alkane. Alkanes are named using the suffix ane, so we add this onto our stem and we have propane. The prop tells us there are 3 carbons in the longest continuous chain, and the ane tells us that this is an alkane, so it's a hydrocarbon with only carbon-carbon single bonds. Next up, we have a compound with 2 carbon atoms in the longest carbon chain that contains the functional group. So we have the stem F. And we have the carboxyl functional group present. The carboxyl functional group is found inside of carboxylic acids, which are named using the suffix oic acid. Now, this is where things get a little bit interesting. We can't just add the oic acid suffix onto the F stem, as we also need to show that the carbon atoms in the main chain are only joined together by single bonds. To do this, we add an "an" between our stem and the suffix, giving us ethanoic acid. Again, the F shows that there are 2 carbon atoms in the longest carbon chain, the "an" shows that they're joined together by single covalent bonds, and the oic acid tells us that it's a carboxylic acid containing the carboxyl functional group. In this example, we've got a carbon chain length of 4, giving us bute as the stem. And then we've got a hydroxyl functional group attached to that carbon chain, indicating this substance is an alcohol. Now, alcohols can be named using either the prefix hydroxy or the suffix -ol. And whenever we have a functional group that can be named using either a prefix or a suffix, we use the suffix wherever possible. Now, in this case, there is no reason for us not to use the -ol suffix, so we do. But just with our carboxylic acid, we also need to show that the carbon atoms are all joined together with single bonds. So we add an "an" between our stem and suffix, giving us butanol. Now, the logical question at this point is going to be, but when wouldn't you be able to use the suffix? And to answer this, we're going to look at an example containing 2 different functional groups. So this substance has a carbon chain length of 4, again giving us the stem bute, but it has both a hydroxyl functional group and a carboxyl functional group. When more than one functional group is present, one group takes priority and determines the suffix of the name. To help us decide which one takes priority, we use a functional group hierarchy. Here you can see a table listing the homologous series in order of priority from those with the highest down to those with the lowest. The homologous series with the highest priority determines the suffix, whilst all other functional groups are later identified using prefixes. So if we compare carboxylic acids and alcohols, we can see that carboxylic acids have a higher priority than alcohols. This means that we use the suffix for carboxylic acids and will eventually use the prefix for alcohols later. So we're going to use the oic acid suffix, again adding in our "an" to show that all carbon atoms are joined with single bonds. For now, we'll write this as butanoic acid because the carboxyl group has a higher priority than the hydroxyl group. In another step later on, we'll come back and add information about that hydroxyl group. The bute tells us it has a carbon chain length of 4, the "an" tells us that all the carbon atoms are joined with single bonds, and the oic acid tells us that we have a carboxyl group present. Now, you might be thinking at this point that looking at that list of priorities wasn't actually necessary, since carboxylic acids only have a suffix and so couldn't possibly end up having to use a prefix. And if you were thinking that, you'd be correct. Some homologous series don't have a prefix, so logic would state that they will always take priority and use their suffix, whilst those homologous series that have both prefixes and suffixes would use their suffix when they're the only functional group present, but would use their prefix when they're not. But this logic breaks down if you have 2 or more functional groups that have both prefixes and suffixes. Consider a molecule that contains both an amino group and a hydroxyl group. Both of these could be named using prefixes or suffixes. So which takes priority? Well, if we look at our table, we can clearly see that in this instance the hydroxyl group would take priority and give the suffix ol, whilst the amino group would later need to be identified using the prefix amino. So we've now identified our main functional groups and used this to add suffixes to our names. However, earlier on we said that IUPAC naming conventions not only tell you what is attached to the main carbon chain, but also where it is attached. And this leads us on to our next step. Step 3 is all about adding locants or numbers to the name to indicate exactly where the main functional groups are located. To do this, we number the carbon atoms in the longest chain that contains the functional group in such a way that the highest priority functional group has the lowest possible number. This will give us what are called locants. They're numbers we can add into our name to show where different constituent parts are located. Let's have a look. So here we have a molecule with 4 carbon atoms in its longest chain that contains the functional group, giving us bute as the stem of our name. Our main functional group is the hydroxyl functional group, which tells us that this molecule belongs to the alcohol homologous series, and as such will have the suffix ol, giving us butanol. Now for the numbering. Well, I could start my numbering at the carbon on the left-hand side, giving me 1, 2, 3, and 4 like this, meaning the hydroxyl group is attached to the 3rd carbon atom. But we're trying to ensure that the carbon atom the hydroxyl group is attached to has the lowest possible number. If I were to start my numbering from the right-hand side instead, the hydroxyl group ends up being attached to the 2nd carbon, which is the lowest possible number we can get. So how do I show that my hydroxyl group is attached to the 2nd carbon atom in our name? Well, I just add a 2 before the suffix, giving butan-2ol. Now there's another important detail for us to notice here, and that is that whenever we are changing between numbers and letters, or letters and numbers, we must always include a hyphen. So we get butan-2 as we're changing from letters to numbers, and then -ol as we change back from numbers to letters. This is really important and can be a common mistake that students make, and unfortunately it would cost you marks in an exam. Let's take a look at another example. So here we have a molecule that contains 5 carbons in its longest chain that contains the main functional group, and that functional group is a carbon-carbon double bond, giving us pentene. If I number left to right, the carbon-carbon double bond lies between the 2nd and 3rd carbon. If I were to number from right to left, then it'd be between the 3rd and 4th carbon, and we're always looking for the lowest numbers possible. So left to right is the correct choice in this instance. But what number becomes our locant? Well, we stick with the rule of always wanting the lowest possible number. So we say that the carbon-carbon double bond starts on the 2nd carbon atom, giving pent-2ene, again remembering the hyphens between letters and numbers. Now there are times where we don't actually need to give a locant to show where a functional group is attached. Let's take this carboxylic acid as an example. It has 3 carbons in the longest chain that contains the functional group, and the carboxyl group is that functional group, giving us propanoic acid. Now in terms of numbering, the main functional group takes priority and needs to have the lowest number possible, so I have to start my numbering with the carbon atom that is part of the carboxyl group as shown. However, the carboxyl functional group can only ever appear at the end of a carbon chain. Carbon atoms can only make 4 bonds, so there is no way of having a carboxyl functional group within a molecule and then continuing the carbon chain. There just aren't enough bonds. This means that whenever you have a carboxyl functional group, the carbon atom in that group will always become the 1st carbon. There's simply no other possibility. So rather than writing propan-1-oic acid, we just leave it as propanoic acid. The oic acid suffix tells us that the substance is a carboxylic acid, which means it must contain a carboxyl functional group. And since that carboxyl functional group can only be located at the end of a chain, it would always become carbon number 1. We don't need the 1 in the name to tell us that, so we don't include it. Now there are other cases where we also don't need to include a locant for the main functional group. This ketone with its carbonyl group, for example, has 4 carbon atoms in its main chain, giving us butanone for our name so far. If I number the carbon atoms so that the carbon in the carbonyl group has the lowest number possible, I need to go left to right, giving us a locant of 2. So at this point we've got butan-2-one, but we don't actually need to include the 2 as there isn't anywhere else in the molecule that carbonyl group could be. It can only be located on the second carbon atom. Now you might think, well, what if you move it over onto the first carbon? Well, if you do, it's no longer a ketone. Ketones have the carbonyl functional group somewhere in the middle of the chain. If the carbonyl group is at the end of a chain, it's an aldehyde, so it would be butanal, not butanone. And you might also be thinking, but what if we move it over onto the third carbon atom? Well, if you did, we'd have to number right to left to give it the lowest possible number, and so it would still be butan-2-one. So since butan-2-one is the only version of butanone that exists, we can simply call it butanone. We only add locants if they are necessary, and the only reason they're necessary is when there is more than one possible location for a particular functional group. So are you wrong to call it butan-2-one? Well, strictly speaking, no you're not, because the carbonyl group is on the second carbon atom. But since that's the only place it can be, you don't have to include the number. And that's why when looking at mark schemes, you might sometimes see locants given in brackets like so. It just means that the locant isn't necessary, but it's not a problem if you have given it. And this brings me on to an important consideration. If you add a locant when it isn't needed, it's not a problem as long as the locant number is correct. But if you don't include a locant when it is needed, then that's going to lose you marks. So if you're ever in doubt, give the locant to be on the safe side. Finally, let's think about an example where there is more than one functional group present. So this molecule has 4 carbon atoms in its longest chain and 2 functional groups, a carboxyl group and a hydroxyl group. Now we actually looked at this example previously and said that the carboxyl group took priority, which is why we ended up with butanoic acid. But we also acknowledged we'd need to add in some information about the hydroxyl group later. Well, this is where an important part of our rule comes into play. We always have to give the main functional group, that's the one with the highest priority, the lowest number possible. So for this example, the carboxyl group has the higher priority, meaning it needs to have the lowest number, so I have to number right to left along the chain. This means the hydroxyl group doesn't have the lowest possible number, and that's fine because it isn't the main functional group. But this numbering system does provide a way to eventually include its presence in the name while stating where it is in relation to everything else in the molecule. And this leads us nicely onto step 4. In step 4, we identify any side chains or lower priority functional groups and add these to the name as prefixes, listing them in alphabetical order with the locant number for each. So here's our previous example back again. We've already established the butanoic acid part of the name as there's 4 carbon atoms with a carboxyl functional group which doesn't require a number as it will always be on the first carbon. We now get to the point where we're going to show that there's also a hydroxyl group attached to the carbon chain and that it's attached to the third carbon in the chain. To do this, we're going to use the hydroxy prefix, and just like when giving the locant number for our suffixes, the number goes before the prefix, separating any changes from numbers to letters with hyphens. This gives us 3-hydroxybutanoic acid. Now let's have a look at another example. Here we have a branched alkane. Its longest carbon chain is 5 carbons long, and it's an alkane, so we have pentane. But we also have this side branch or side chain that we need to consider. Now these side chains or branches are called alkyl groups, but the name we give each one needs to indicate how many carbon atoms there are in the chain. The names we use for each of these side chains is based upon the same naming conventions we used when determining the stem of our molecules, only we add "-ile" onto the end. So if we have an alkyl group made up of one carbon atom, sometimes known as a CH3 group, we'd call it a methyl group. Two carbons, sometimes shown as a C2H5, ethyl, and so on. Although you can get side chains of varying length, for the molecules you're going to be naming, you're unlikely to be going much higher than a propyl group as a side chain, as you're limited to stems of 6 carbon atoms or less. So in this example, I have a methyl group attached to my pentane molecule, but I need to state where it's attached. In this case, it's attached to the middle carbon atom, which would always therefore be the third carbon, no matter which end I started my numbering. However, it's worth considering at this point that if it wasn't in the middle, we'd want to number the carbon chain so that the methyl group has the lowest number possible. This gives us the complete name of 3-methylpentane, again separating numbers and letters using a hyphen. Now let's look at an example where we actually have multiple prefixes. This molecule's longest chain is also 5 atoms. However, notice that there are actually 2 different ways we could trace a 5-carbon chain through this molecule. Both are valid longest chains, and whichever one we choose, we end up with exactly the same IUPAC name. And that's because IUPAC naming describes the structure of the molecule, not the way we've chosen to draw it on the page. I'll show both examples as we work through so you can see this in action. So in this instance, our main functional group is a halogen atom attached to the carbon chain, telling us we have a halogenoalkane. Now, halogenoalkanes are a little unusual because they're named using both a prefix and a suffix. The prefix tells you which halogen is present, and the suffix is -ane to show we only have single carbon-carbon bonds. Now, like in our last example, the bromine atom is in the middle of the chain, which means that regardless of which side I start numbering from, it will always be on the third carbon atom. However, in this instance, I do have to number from left to right, and that's because of the presence of the methyl group. As an overriding principle, we always want as many groups as possible to have the lowest locant numbers they can. Numbering from left to right would give the methyl group a locant of 2. If I went right to left, it would give it a locant of 4. So although it's not the main functional group, I still want it to have as low a number as possible, so we number from left to right in this case. And the same would apply to our chain with a bend in it. We want this methyl group to have as low a number as possible. So having numbered our chains, both examples give us 3-bromopentane. Now we need to add the prefix for our methyl group, which again in both examples is located on the second carbon atom. See how it doesn't matter which carbon chain we started with, because both routes satisfied the condition of finding the longest carbon chain that contains the main functional group. Now, as our rule states, all prefixes need to go in alphabetical order. At this stage, it doesn't matter whether one group has a higher priority than another or what the locant number is. We're solely interested in arranging the prefixes in alphabetical order. So B comes before M in the alphabet, so our bromo prefix comes before our methyl prefix. This gives us 3-bromo-2-methylpentane. Again, making sure we include hyphens every time we're changing between numbers and letters. And it's at this point you almost start to feel like a proper chemist. These are the kinds of names you see on labels that read as if they've been written in a completely different language. But by understanding how these names are derived, they just start to make sense. So one last example before moving on to our final step. This molecule has a carbon chain length of 5 and contains the carboxyl group as its highest priority functional group. From steps 1 and 2, this gives us pentanoic acid. Following step 3, we number our carbon chain so that the carboxyl group has the lowest possible number. This still leaves us with pentanoic acid, as I don't need to include the locant for the carboxyl group as it has to be attached to the first carbon. Now for step 4, there are 2 additional functional groups we need to consider, a hydroxyl group on the third carbon atom and an amino group on the fourth carbon atom. So again, we put these as prefixes with their locants in alphabetical order. We don't worry about priority, we don't worry about locant numbers, we solely focus on alphabetical order. This gives us the complete IUPAC name of 4-amino-3-hydroxypentanoic acid. But what happens if we have 2 of the same functional group or side chains attached? Well, that's where our fifth and final step comes into play. If there's more than one identical side chain or functional group in the molecule, then we add an additional part to the prefix depending upon how many of the identical groups there are. Di for 2, tri for 3, and tetra for 4. Crucially, however, these additional parts of the prefix do not affect the alphabetical ordering of prefixes. Let's take a look. So going through our steps, firstly, longest carbon chain containing the main functional group is 5 carbons long. This gives us the stem pent. Then, main functional group is the bromine atoms, telling me I have a halogenoalkane. This means I would use the bromo prefix and ane suffix, giving bromopentane. Step 3, number the chain, giving the main functional group the lowest possible numbers. So I need to number left to right, giving 2 and 3 rather than 3 and 4 if I went from the right. Step 4, prefixes. Based on what we've said so far, this would give 2-bromo, 3-bromopentane. But for step 5, I can simplify this and add a di to the prefix. This would give 2,3-dibromopentane. Notice how the locants for each bromine atom is separated by a comma, and there's the hyphen as we change from numbers to letters. This is our full IUPAC name. But what if we have multiple identical groups attached to the same carbon atom? Well, we just follow the same process. Longest carbon chain containing the main functional group is 5, giving us pent as our stem. The only functional group present is carbon-carbon single bonds, telling me it's an alkane, so we add the suffix ane, giving pentane. Numbering-wise, it's these additional side chains that are going to dictate whether I number left to right or right to left. I want to give them the lowest possible numbers, so I need to go left to right, so they're both attached to the second carbon. Step 4 would mean we add the methyl prefixes, giving 2-methyl, 2-methylpentane, which immediately sounds odd and like you're just repeating yourself. So we include step 5 as we have identical side chains, finally giving us 2,2-dimethylpentane as our complete IUPAC name. Notice that both locant numbers have been given. I can't just say 2-dimethylpentane as that doesn't state where both methyl groups are. The important thing about IUPAC names is that they leave no room for ambiguity, so we have to give the locant numbers for all relevant parts. Finally, let's look at an example where there are 2 different groups that need including as prefixes. As always, we'll just follow our steps. Longest carbon chain containing the main functional group is 5 carbons, giving the stem of pent. The highest priority functional group is the bromine atoms, telling me it's a halogenoalkane. I use the prefix bromo and the suffix ane, giving bromopentane. Next, numbering. I want all of the bromines to have the lowest numbers possible, so I number left to right. I then think about the methyl group and put my prefixes in alphabetical order. B comes before M, so the bromo prefix must come before the methyl prefix. Applying step 5 lets me group the bromos to give 1,1,2-tribromo 3-methylpentane. Now there's a few important bits to note. Firstly, whenever you're changing from letters to numbers or numbers to letters, you must always include a hyphen. Secondly, the locant must be given for each size chain or additional functional group. I've given the locants for each of the 3 bromine atoms as well as the locant for the methyl group. And lastly, notice how the tri prefix for the bromines hasn't impacted my ordering. It's the B and M that I'm comparing, not the T and the M. Okay, so as an overview of the entire process, when naming organic compounds, the first thing you do is find the longest chain that contains the functional group. This gives you the stem. Then identify the highest priority functional group to get the correct suffix. Number the carbon atoms in the chain so that the main functional group has the lowest possible number. This gives your locants. Add on any prefixes for side chains or lower priority groups, putting them in alphabetical order with their locant numbers. Finally, use the di, tri or tetra prefixes if necessary, giving the locant numbers for all groups, even if they're on the same carbon atom. One of the really nice things about IUPAC nomenclature is that the process works both ways. So far we've been looking at structures and using them to generate names. But because each part of an IUPAC name contains structural information, we can also work backwards from the name to draw the molecule. And you'll absolutely be expected to do this in an exam. You start with the stem of the name to determine the length of the main carbon chain. Use the suffix to identify the main functional group and attach it at the position indicated by any locant. Then work through the prefixes, adding any side chains or lower priority functional groups to the carbon atoms specified by their locants. So if we take 3-bromo-2-methyl-butan-1-ol as one final example, I look at the stem, but. This tells me there are 4 carbon atoms, and because of the an, I know they're all joined by single bonds. The suffix ol tells me it's an alcohol, and so I need a hydroxyl group, and because of the 1, it needs to go on the first carbon in my chain. I'm going to start numbering from the right hand side, making that carbon number 1, so I add the OH group onto my first carbon. Now I can just work through the prefixes in turn. 3-bromo, I need a bromine atom on my third carbon, remembering to stay consistent with where I started my numbering from. So there it goes, on the third carbon from the right. 2-methyl, well, I need a methyl or CH3 group on the second carbon atom. And there we have it. So that's all the parts of the name covered. Now I just go along the molecule, adding hydrogen atoms until all carbon atoms are making 4 bonds. If you're doing this with a molecule that contains any double or triple bonds though, just be careful you don't get carried away and add too many bonds. And that's how to name and draw organic molecules using IUPAC nomenclature. In the next lesson, we'll start looking at reaction mechanisms and the conventions chemists use to represent how reactions actually occur.